without inheritance. Okay, so if we have a range of integers from -100 to 100, then a range from 0 to 100 would be a sublet. Yes.
Sorry, would you mind putting on your microphone?
Again?
Your microphone?
Oh.
Thanks.
Subtyping is a specification concept. It doesn't have to do anything with inheritance. And subclassing is one of the methods to create types from existing types. But subclassing implies that we are creating a subclass, right? So it's an implementation concept related to specific mechanism in object-oriented programming languages that allows us to create classes from existing classes. So this is subclassing. And we looked at a very important example that showed us that if we use subclassing, what we end up with is, of course, subtypes, but they are not necessarily true subtypes. So it is possible to create subtypes which would not be true subtypes. And we listed all the, there was a bunch of rules that define what a true subtype is. Basically, the entire list of substitution principle is just describing those rules. If we look at the overall picture, it's all about substitutability. So if A is a true subtype of B, then we can substitute A for B in all contexts, right? And all the other rules, like do not throw exceptions which would not be subtype of exceptions that were thrown by their super type. All those rules, it's just clarifying what it means to be substitutable, like what we have to ensure in order to guarantee that A would be substitutable for B. All right, and then we talked about overloading and overriding. All right, from the practical perspective, these are two very important concepts. Overloading is creating implementations of methods with the same name as an existing method, but different parameters. And overriding is providing a new implementation to a method that we inherited. So when we override, we cannot change the parameters, right? The parameters have to be the same. But the return type can be different. The return type can be a subtype of the return type in the method that we are overriding. So for return type, this is called supporting covariance in return types. So return types can be covariant. And then we looked at the general picture, and we discovered that while a specific programming language, Java, does not allow contravariance in parameters, in theory that would be allowed, right? And there are programming languages that do support that, right? So yes, we can actually allow subtypes to define methods that would have different parameters, but then these parameters have to be more general types than the parameters in the method that this method overrides. And it kind of makes sense why Java designers decided not to allow contravariance in parameters, because that could clash with overloading. Right? If we do allow contravariance in overrides, how would we tell the difference between overloading and overriding then? Right? So it was just easier to not allow overriding methods to make any changes to their parameters. All right, so then we reviewed some of the examples which showed how classes can be a little intimidating. If we're not careful enough implementing our methods, then in the presence of a hard if classes, we might see some subtle issues. All right, one set of issues was related to immutability. So, for example, if we use a mutable type for any hashable data as the key for any hashable data structure, that creates a problem, and we looked at that. All right, so here is another example along the similar vein. Let's take a look at it. So we have my class that has equals, which takes my class, so it's an overload, not an override. And then we have a hash set with a key with elements as objects of my class. Okay, and then we add two objects, my class, freshly created, and then we check the size, and it's 2, right, as it should be. And then what happens is if we compare these two objects, right, so if we compare it like that, we get true. If we extract that object, right, so the two objects have to be equal always, right, so our implementation of equals is very primitive. It always returns true. But it turns out that here equals returns false. And that tells us that it's not our equals, right? It's some other equals, not the one that we implemented here. That explains why this is dangerous to provide an overloaded equals, right? Because then code becomes completely confusing, right? But the answer here is that the implementation inherited from object is actually invoked here, and since these are two different objects, right? O is this an object, and new my class creates another object, so there are two different objects. That's why equals returns false. All right, so you would kind of expect all instances of my class to be equivalent. That's not what is going on here, and we have to be careful with this, right? So when we override, we redefine the method. We provide another implementation. When we overload, we do not replace anything. We just supply a new method, right, or a new version of the method. All right, so in this we briefly touched upon why Java doesn't allow contravariant parameters and overrides. Right, because then it would be confused whether it's an overload or an override, right? And that would be just confusing unless we make some other changes to how the language is designed. Right, and here are two languages as examples that do allow contravariant arguments. OCaml and Sether, not the most popular languages, but OCaml you might have heard actually. All right, and this is their example that we already reviewed, right, from Homework 0, bulk container and box, and we already established that the box is not a true subtype of bulk container because we could not substitute box for bulk container, right? It guarantees less, and it returns false in cases where it's a super type, right? If we're thinking that bulk container is a super type, would return true. So no, it's not a true subtype, and the client would be justified to write this code, right, using their bulk container, and this code would work with bulk. If here we had a bulk container, right, this code would run, and then if we substitute box for bulk container, then it's not going to work the same way, right? It would return false in cases where the super type bulk container returns true. So no, it's not a true subtype. All right, so we talked about Java subtypes and true subtypes, how dangerous it can be when we have Java subtypes which are not true subtypes. Again, Java language compiler is not going to help us in true subtypes. It's completely on you, right? You have to make sure that all the subclasses you create are true subtypes. Of course, if you violate this recommendation, your code might work or work to some extent, or work with some, some particular features, right, with some strings attached. But it is best that the code would be easy to read and robust if all your Java subtypes, all subclasses that you create in Java are true subtypes according to our definition. Right, so when B is a Java subtype of A, ensure that B does not remove any methods from A. And not like we actually can remove any methods from it, right? But if you see that you inherited a method and you want your client to be unable to call this inherited method, that means that you feel the urge to remove this method, right? And that tells you that no, it's probably not the right hierarchy that you created, so it's not a true subtype. So then for every method in B, a substituting method in B has to have a stronger specification than the corresponding method in A. Right? So for all methods, if some method M in B does not have a stronger specification than method M in A, then it would break substitutability, and it would not B would not be a true subtype. So we want substitutability, and if you follow these rules, then you are guaranteed that B would be always substitutable for A. Right? And this is what LSP, list of substitution principle, is about. It's a principle, right? It's not a command. So just remember that it applies not just to Java, right? It's just the kind of computer science theory or software design theory that applies universally. And of course, specific programming languages like Java may decide not to implement it fully. For example, Java does not allow contra variants in parameters, and this is fine. Right? So you just need to be aware of those differences. All right. So back to specifications. Remember, we way back. We were saying when we just started talking about specifications, we noticed that even if we do not write any specification, then by just looking at the code, we still know something about a particular method, right? We have the types. So type signature is a form of specification. Yes, it's it's not particularly strong, right? For example, we cannot say that this I is between 0 and 5. Okay, saying int, just reading their specification, their signature, right? We see that it's an integer, so it can be any integer, but it's still better than nothing, right? So it is a contract too. So we can extract this specification information from the header of the method. So we can say precondition tells us that s is a string, I is an integer, and postcondition that the result is double. Again, we don't know anything else by just looking at the type specification, but still, this is better than nothing. So that tells us that we need to be reasoning about the behavioral aspects of our code and the effects that this code has or might have on the objects in the system, right? And that's why we added these 5 keywords: requires, effects, modifies, returns, throws, right? Because we needed a better and more advanced language to describe specifications. All right, so now think about the true subtype definition, right? That we just came up with. True subtype, this definition applies only to types, right? Not to individual methods, right? Remember how we're saying A is a true subtype of B if we can substitute A for B, meaning that A and B are types, for example, classes in Java. But we can sort of carry over the same concept of true subtyping to individual functions, and we call it function subtyping. Right? So what it is substitutability, but not at the level of their types, like entire classes, but at the level of specific functions. Right? So imagine that we have functions f in A and f in C, and we are wondering under what conditions would f in A be substitutable for f in C. All right? And if their function is substitutable, it would be called a function subtype. So we reason about functions at the level of the type signature. Okay? Here are the rules. First, f in A has to be a function subtype of f in C in order to be substitutable. Right? That's basically why we introduced this new term, function subtype. So what it means for a function to be a subtype of another function is that the return value is a sub of the function that is a subtype. Right? So A in this case has to be a subtype of the return type of the function that it is substitutable for. So we are hoping that f that returns A is substitutable for f that returns C, and the first rule that ensures that is that the return type of f, which is A, has to be the subtype of the return type returned by this f, so C. Right? And then with parameters, it's in the opposite direction. Right? So B, the parameter type, has to be a supertype of D in our other f, the f that returns a C. Right? So A and C are return types, B and D are argument types, and for function subtyping, we see that as far as the Java language is concerned, it's not going to be overriding. Java would treat function subtypes as overloads, okay? Because here we see that parameters B and D, they are different types. So that tells us that, well, out of all the overloads, we have now two groups of overloads. One where there is no relation between the parameters, like these B and D are not related, so they're just overloaded methods, and there's nothing else we can say about them. But if it turns out that these overloaded methods, B is a supertype of D and A is a subtype of C, then these two overloaded methods, we would call that method on the left, method that returns A, that takes B and returns an A, would be called a function subtype of the method f that takes a D and returns a C. Right, so basically it means that A could be a subtype and B, so a subtype of C, or it can be C itself. And B has to be the same type as D or a supertype of D.
So is the idea essentially that A has to be, is that it's kind of playing into what we know about specifications, where the parameters, aka the requires, has to be less specific, but the what you return has to be more specific?
Yeah.
That's right.
Yeah, so exactly, this is contravariance for parameters, covariance for return types. Okay? But now Java would support it because for Java it would be overloaded. All right, so that's that. And then of course B could be a supertype of D, and A could be the same type as C. So bottom line, of course, A cannot be the same as C at the same time as B is the same as D, because then there would be no difference between these two functions, right? So either A has to be different from C, or B has to be different from D, or they both have to be different. All right, so yeah, from the standpoint of specification, right, return type has to be stronger, argument type has to be weaker. and we immediately recognize, oh, that means a stronger specification. So yeah, this whole thing hopefully makes sense, right? So if we are saying that this f that takes b returns a is substitutable for f that takes d and returns c, it means that this f that takes b and returns a has a stronger specification. A stronger specification meaning that their precondition is the same or weaker, and the postcondition is the same or stronger. This is our old definition of substitutability by just looking at specifications. All right, so the type signature substitution method has to be stronger.
Can you have it, I think you mentioned this, but I'm just so confused on it. Can you have it where a type is a subtype of itself? Like, you kind of like compare, say like A and B are the same and C and D are the same?
Well, if A is the same as C and B is the same as D, then it's the same. You cannot have two definitions for the function with the exact same signature.
Okay.
Right? So that wouldn't be, because how would it then decide which implementation to use? All right. Yeah, and that just means that for parameters we have contravariance, and that means that the reason contravariance is allowed is because it places no extra requirements on the client. Right? So if previously the client was sending us a string, and in their function subtype that we are trying to substitute for the old function, their new function is an object. A string is an object, right? So the client that was sending string is still sending string, and our code still works. All right, so that is perfectly fine, right? So we need to think of parameters and the return type as part of the method specification, right? And think of the arguments as a precondition and the return value and throws as their postcondition. So their subtype should have stronger specification, which means for arguments we have to have weaker constraints, which means more general types, and for supertypes and for return types we have to have a stronger postcondition, right? So stronger, more restrictive types. That is subtypes of their return type of the function that we are substituting for. All right, so here is an example, right? We have here animal and giraffe that extends animal, and then just the driver code that shows us what is going on. Right? So we create an animal and giraffe, two objects, but note that variable g is of type animal. And when we attempt to invoke say hello from G, okay, it is a compiler error passing A as an argument. Let's try to understand why. So the declared type of G is animal. So we go to animal, and we are looking at say hello that would take an animal. There is no say hello that would take an animal in animal. There is no such method family. And it doesn't matter what happens in their subtypes, right? There is just no matching method family here. Say hello does not have an overloaded version that would take an animal. That's why it's a compiler error. Right? So what if we pass G? Right? Same story. It doesn't matter that G actually contains a giraffe object. Right? G is declared, so its declared type is animal. Right? And therefore, we cannot risk the danger of assigning an animal to G giraffe. Right? Because that in general is not going to work. It's not going to be safe. All right. So contravariant arguments, they do not work in Java overrides. Right. So say hello is an overload, and at compile time, both A and G belong to the animal class. It doesn't matter that G has a runtime type of giraffe, doesn't matter, right? There is no method, say hello, that takes an animal in class animal, right? Yeah, that's it, right? So for Java, it just ends here. So Java treats contravariant arguments as overloads, not as overrides. It determines the compile time based on the analysis of the method families, once the method family is determined by the compiler, it's not going to be, this decision is not going to be questioned again at runtime. All right, so that basically covers the contravariance of parameters. So now for covariance of the return types, right? It's a little easier because Java does support it. So we just have to make sure that the specification of the replacing method in B does not violate expectations of the client, which means, among other things, that no new exceptions can be thrown. Existing exceptions can be replaced with their exception types, which are subtypes. Right? So if our M in A was throwing exception, then M in B may throw illegal argument exception, which is a subtype of exception, right? But not in their opposite direction, right? Because again, their specification of their replacing method, the substituted method, has to be stronger, which means that their post condition has to be stronger as well. All right, and here is an example to show covariance, right? So here we have two methods, clone it, that create a new object, which would have the same name as the existing object, then we see that, yeah, it works perfectly fine, right? So we call clone it on A, right? And it returns a new animal, we assign it to G, which is an animal, right? But what would be their actual type of whatever is in this variable E? Well, let's take a look. We have A, which is a giraffe, okay? So their static type of A is animal, their runtime type of A is giraffe. So when we call A.clone it, at the compile time, we are going to be only looking at the animal class because A has a type and has a declared type of animal. So we are trying to find if there is a matching method family, and there is clone it that takes nothing, returns an animal. So this method family is going to be selected as the method family to invoke. But then at runtime, we will look at the runtime, JVM will look at the runtime type of A and see, well, within that method family, maybe that method was overridden. And sure thing it was, right? This clone it is overriding the clone it that giraffe inherited from animal. And therefore, this clone it will call the overriding version, this version that creates a new giraffe, right? Therefore, G would have a runtime type of giraffe. When we then say G, say hello, okay? Well, say hello, we assume that their definitions are the same as they were on the previous slide, right? So it would just invoke say hello on, is it the same? Hello? No, it's a different, it's actually skipped, but say hello just prints name, okay? If you look at their covariance.java, the full example, right, then it has, of course, all methods named. So when you here you say hello, it will print the name of the Alice, which is the giraffe. All right, so core variant return types are allowed in Java. That would be overriding methods, and resolution of a method calls would be two-stage. First at compile time, then at runtime. So the final save is dynamic. The final save would be determined at runtime. All right, so with the Java overrides, we have covariant return types, and argument types have to be exactly the same. That's why we say argument types are invariant. All right, more examples of subtyping, and let's look at the class from the JDK hash table, and it has put and get methods, and then let's imagine that we want to extend hash table, create a subtype of hash table, so that in addition to just basic functionality, put in get, right? We also have something else, right? So we have some properties, right, that we want to be more type specific than they are in hash table. So hash table, if we're using the raw type, not the generic type, but the raw type, then put has parameters of type object, get has parameters of type object, the return type of object. Right? So what if we want to have more specific key value like strings? Okay, so that would that would be right. So that would be the implementation that we would be able to come up with, right? So override, put, override, get. All right. Another example: we have product and we have sale product, right? With method recommend overriding recommend that was inherited from the parent, from the superclass. All right. Let's see. This recommend that returns a product and takes a sale product. Is it an override? No, it's an overload. It would work, right? So this code would compile. There would be no error, but it's not going to be an override. Right? It's not going to be a function subtype, right? It would be overloaded. All right. Then this recommend that takes product returns sale product. Well, that would be a true subtype, right? Because and it would compile, of course, just fine in Java, right? Because we see covariance in return types and invariance in argument types. Option number 3, recommend that takes an object. So that would be okay in general, right? Because from the standpoint of the function subtype definition, we can replace the type of the parameter with a more general type. So we can replace product with an object. So that would be a true subtype. That would be a function subtype. So this recommend would be a function subtype of this recommend. Whereas this first recommend would not be a function subtype of this recommend, right? Because we have covariance in parameters, not contravariance.
So does that mean that then number 3 would be a valid override, or would it still be an override?
No, it wouldn't be a valid override in Java. It would be overload,
Okay.
right? But if we are asking, it's very important to see, to read the question, what the question is asking about. Is it asking whether this code would compile in Java? That's one question. The other question might be, would that be a function subtype? Okay? And well, the two questions might be combined together, right? So you might be asking, is it or not a function subtype? Would that compile in Java now? So all 3 first options will compile in Java. The first one would not be a function subtype, but it would compile in Java. It would be an overload. The second one would be a function subtype, and it would compile and work correctly in Java. The third one would be a valid function subtype, but because contravariance in parameters is not allowed in Java, it would be an overload, not an override. But it would work. It's just not going to be substitutable as far as Java is concerned, right? Because it's not going to be overriding recommend that was inherited from product. All right, and finally, this one, the fourth one, right? So no, it's not a function subtype because it throws exceptions that their original method, the recommended product, wasn't throwing, right? So that's not okay. What about Java? Right? It's also not gonna compile because it's an identical method. So you see that parameter types and return types are the same, but this throws a new exception, right? So when you override, you cannot throw exceptions that the method that you are overriding was not throwing. So IO exception is not compatible with the throws clause of recommend in product, because the throws clause of recommend in product has nothing. Right? There is no throws clause, which means it does not throw any unchecked exceptions. Whereas this no sale exception, we assume it's a checked exception, right? No, it cannot override recommend in product because it says it throws an exception, which that one was not throwing the recommend in product. All right, so let's try to sort of summarize what we've talked about. So we are reasoning about the specifications at different levels. So we have two important definitions: true subtype to compare to judge the substitutability of entire types, and function subtyping, right, a smaller scope, a definition that allows us to judge on the substitutability of functions. Okay, and function subtyping is about type signatures, so implementation doesn't matter, right? So it's all about the specification. Remember, type signature is the specification. So compiler checks function subtyping when you compile the code, and behavioral specifications are expressed by our 5 keywords: requires, modifies, affects, returns, and throws. Right, so in order to ensure that A is a true subtype of B, we must reason about behavioral specifications, about how these two types behave. And that means that we have to look at all the methods in A and B. Okay? And if they all exhibit the same behavior, then A would be substitutable for B, and that would mean that A is a true subtype of B. This subtyping, right? Again, here's just another angle at which we can look at this definition of the true function subtype. It's a behavioral subtype, which means that if we compare side to side M in B and M in A, then M in B would be a true function subtype if these conditions hold: contravariance for parameters, covariance for return types. Okay, these two conditions guarantee that the specification of M in B is stronger than the specification of M in A, and therefore M in B is substitutable for M in A. Of course, we are assuming that all other things being equal. All right. So now a little, let's from this theory, let's get a little down to earth and talk about how we actually write our Java code to incorporate all the things that we just discussed. So in Java, we have primitive types and classes, and then we have interfaces. Okay, so yes, classes can be abstract or non-abstract, that is concrete, but other than classes, interfaces, and primitives, we don't really have much else. So when we want to create a Java subclass, we either use extends or implements. So if we are subtyping from a class, right, so we are creating a subclass of a class, so B extends A is a class. If we are extending from an interface, in Java terminology, they say we implement an interface. And that's why if A is an interface, then we would write B implements A, right? So in Java terminology, substituting method is an overriding method, right? Because we know when we create an overload, we do not replace, we do not substitute, we just add another method. So overloading is not the same thing, right? Therefore, we have to be careful with that. When we override, Java does not support contra variants for parameter types, so parameter types have to be invariant, have to be the same, but the return type can be the same or a subtype of the return type in the method that we are overriding. Overriding method cannot have any new exceptions that were not part of the specification of the method that we are overriding. It may replace existing exceptions with their subtypes of those exceptions, but it may not introduce any new exceptions or replace existing exceptions with their supertypes, because that would weaken the specification. All right, so let's now go back to our example with hash table and a subclass of hash table that we called properties. Right? And what we wanted to do is to create a sort of more specialized version of a hash table that would operate on strings rather than objects. Right? An object is not really a very convenient thing to deal with because it basically has no useful methods. Right? It's so general, it's so basic that if we have an object and the only thing that we know about it is that it's an object, big O object, then you can't do anything with it, right? So you can only have a very basic set of methods that you are able to invoke, like equals to string, hash code, and a bunch of others, but nothing really domain specific, nothing really useful, right? So that's why we wanted to create a more specialized version of hash table. But when we implemented it like that, you see that we ended up with two put methods and two get methods because we have overloading in Java, right? So this put method is not replacing the put method that properties inherited from hash table. It adds to it, right? And that of course it might be causing a problem, right? Because now we have two method families. Here is an example for put, but for get, it's the same story. Then which method family is selected depends on the declared type of their variable. So we can no longer enjoy our homomorphism fully, right? Because then depending on how we declare the variable, it would switch from one method family to another. Right? If our key is declared as a string, we would call this method family. If we wanted to have a more general variable for key and made it an object, all right, an object may contain a reference to string, right? There's nothing wrong with it. But then all of a sudden, when we call put, it switches to this other method family, right? So that's not good. All right, so that we already mentioned, right? We already discussed method families and how method resolution works for overridden methods. So there are two types, compile time type and their actual or runtime type. So the compile time type is also known as declared or static or apparent, all right, type. Basically, this is what is written as the type for your variable, right? So this is the name of the type that in the declaration of your variable is preceding the name of the variable. It is given once, and in Java it can never change, right? So if you declared A as a properties, right, you cannot change the type of that variable ever. The runtime type is the type of the object that this variable actually references. And of course, it is dynamic, it can change over the course of the execution of our program. Right? So if we have a variable of type object, it may first refer to an object of type string, and then we assign it to, we assign date to it, so now our variable points to an object of type date. Then we assign another reference to it, so it starts pointing to yet another object, right? So that's why it's dynamic, and that's why it's called the runtime type, right? Or the actual type, or the dynamic type. All objects in Java are allocated on the heap. Right? This is actually a very important piece of information because, for example, in C++, that is not true. Right? In C++, you can have objects allocated on the stack. Right? And objects that are allocated on the stack, you access them without using any references, right? Because they're just like local variables on the stack. In Java, this is not possible, right? In Java, there is no way to allocate an object on the stack. So all objects, without any exceptions, are created with the new operation, and they are created in the heap, and that means you can only access that object through a reference. All right, so runtime type, of course it can be the same as compile time type, or it can be a subtype of compile time type. Again, think about object and string, date, point to the hash table that you can, all the different types of objects that this variable type object can actually refer to. All right, so static and dynamic types, right? So B extends A, C extends B, so basically we have an inheritance hierarchy, right, where we have A and then B and then C. So the dynamic type of an object is the type of the object that was assigned to this variable. Right, the static type is what is written in your source code to the left of the name of the variable. Right, this is the static type or compile time type or a parent type. All right, so Java subtyping guarantees. Right, so Java. Remember again, going all the way to one of the first lectures, we were saying that Java is a type-safe language, unlike, for example, C++. It means that Java gives us certain very nice guarantees, and these guarantees are worth a lot. So their subtyping guarantee says that if this code compiles, it is going to run, and it is not going to. It is never going to create an undefined behavior situation. For example, when a method is invoked on an object that does not have that method, right? Remember, it was totally possible in C++. It's not possible in Java. It doesn't mean that everything can be detected, can be checked at compile time. No, right? In Java, the subtyping guarantee is a combination of compile time checks and runtime checks. So compile time checks, if they're not satisfied, your code would not compile. All right. So of course, this is the preferred outcome because then we know immediately that something is wrong. But checks that are not feasible to perform at compile time, they are performed at runtime. And then if one of those checks is not satisfied, we get an exception. For example, last guess exception. Right. So it is still, a way of protecting us, okay, from the standpoint of the language of Java, right? Because when that exception was thrown, it means that the dangerous statement was not executed. So the exception was thrown before an attempt to execute a statement, which would lead to undefined behavior. All right, so here is a short example, right? We have variable type O. It can totally contain a reference to a date object. All right, and if we swap the types, then no, it's not going to work, right? The reference to a date object may only, the variable of date type may only contain a reference to a date object or an object which is an instance of one of the subtypes of date. Right? Object is not a subtype of date, object is a supertype of date. That's why this is a compile time error. All right, so now we more or less already discussed this, right? But let's repeat it. So how does method call execute? How does this resolute method invocation resolution process goes? So for example, we have this statement x.foo with 5. So first, is going to be compile time. Second is going to be runtime. Remember, it's always two parts: compile time and runtime. Right? So at compile time, the compiler is going to first check the type of X to determine which class to look in for this foo method. Then it will analyze in this class, it will look at all methods foo, and these methods will all be different by parameter types, right? They can only be overloads, right? So each overload will be its own method family. So then the compiler would take into consideration their parameters, or one parameter in this example, and select the method family that would work. A very important observation here: it would select any method family that would be, that would work. For example, if there's a method family that says foo that takes an int, yeah, great, it's a perfect match. But what if we have foo that takes an object? Would that be, and let's say we do not have foo that takes an int. Would foo that takes an object work? Yes? No? No? Yes?
I feel
I see you saying no.
Yeah.
Does anyone want to say yes? Think about auto boxing, right? So a primitive value 5, an integer, can be represented as an object of type big I integer, right? And all objects, all classes in Java are subtypes of big O object. So integer is as well, right? So after auto boxing, foo that takes an object would totally work, right? Because we can assign an integer object to a variable type object.
Oh, so if you say object X is equal to 5, then an autobox is 5 into an integer object?
No, what I mean is, well, X is just, X is kind of irrelevant, right? So for now, at compile time, we only need to know the type of X to determine the class in which we are going to be searching for foo, right? So let's say X is defined like that. So we go to class A and we look at all methods foo in A. So if there is a foo that takes object A, then that would be a valid match for this call, right? Because an integer is an object, right? So the important observation here is that at compile time, when we are here, the compiler is trying to find a matching method family. It doesn't have to be an exact match, type for type, right? It can be, just any match that would work given, our polymorphism, right? Given the fact that, this type can be a super type of this type that we have in the parameters, okay? However, it's very important. Their match has to, so this method family has to be exactly one method family, right? What if there are two method families that work equally well? And I think we reviewed, I showed you a little sketch, a little example last time, right? Imagine that you have method foo that, with one argument, it's not going to happen. But let's say we have foo with two arguments: string and object and string. Two overloaded versions, right? Two overloaded methods. And then you have a call foo, string 1, string 2. Right? That would result in a compile error. Why? Because both method families, they match equally well. None of them matches perfectly, right? Because none of them has both parameters match exactly, right? So one parameter matches exactly, the other one does not, but is still compatible. Okay? So both method families would work equally well. The compiler cannot break this tie, and it just fails to compile the code. Okay? So this method family, right, we are in trouble if we don't have any single compatible method family, or if we have more than one, we are also in trouble, right? It has to be exactly one best method family.
Oh, there's a question over there.
Yes, please.
So you said that if you put slide like an object O, you said it was still working, right?
Yes.
So I'm kind of curious about that because the integer class has properties that the object class doesn't. So
Yeah.
you can use those properties inside.
No. No. Because if our foo declares this A as object, it would only have access to whatever object has. It would not have access to, it would not be able to do A dot value of, for example, right? Because there is no value of in object. There is value of in integer, but a foo here doesn't know that A is an integer. It only knows that it's an object. What it could do, right, it could check, with instance of or get class, hoping that this A, maybe it's an integer, but it has to check first before it casts the type of A from object to something else. Remember how we did that with equals?
So is it the way that x.foo5 works is that it tries to find foo that takes in an integer, an int, it's like, I can't find that, tries, and then it's like, okay, I'll try autoboxing it, autoboxes it, finds object, it's like, there, I'll use that.
Say it again, please.
So is it like, I'm just confused on how like, when it autoboxes 5, like does it autobox 5 immediately, or does it first try to find a foo overload that'll take in an int, can't find that, then it tries to autobox
Yeah, so it will autobox it here. So it will actually change this call to say x.foo new integer 5. So it would autobox it right here.
So then if there existed a foo overload that took in like an int, non-integer object, would that still match with that then? If it then autoboxes it? Like I'm just confused on like how that match would happen.
Yeah, if we have foo that takes an int and foo that takes an integer, then there would be only one best, for this call, there would be one best option that matches exactly foo that takes a primitive int. Alright, so we determine, or the compiler rather, determines the method family by just, listing all the methods and finding all their methods with this name foo. Note that it would include all inherited methods, right? Of course, you don't have to repeat the implementation of the methods that you inherited in the subclass, right? But again, if you're solving a problem, you might want to actually list them to make sure that you don't overlook those inherited methods. Right, so then we look for overrides. The return type may be a subtype, again, covariant return types. And we only keep methods that are accessible. So remember, we have the access modifier, private, public, no modifier, which can be a game changer. So if the method is there, but we cannot access it, it's like it's not there. All right, and then it would keep the most specific type. Okay, so out of several options. If there is a perfect match, it would go with it. All right, so then at runtime, the type of the actual object is determined, right? So this variable, right, it's a reference variable. The actual type of the object, we call it the receiver object, is determined. Right, so for X, in this case, what is the type of object contained in the set? And then the runtime environment, Java runtime, would look at all the overridden methods in that method family and decide which of the overridden methods from this family to actually call. It would call their closest, from the standpoint of their inheritance hierarchy, the closest overridden method. So let's say we have A as a superclass and B, C, and D. Right? And let's say the runtime type of the object is D, and the method is overridden in C, but not in D. Right? So the method was declared in A, then just inherited in B, not overridden in B, then overridden in C, and then not overridden in D. So if the runtime type object is D, then it will use the overridden version from C, right? Because it inherited their latest overridden version from its most immediate parent. All right, so important is that method family is never going to be changed at runtime. Whatever the compiler decides regarding the method family, that method family, and only that method family, is going to be used. All right, so here is an example. Right, we have general animal, talk. We have bird that overrides talk, car, cat that overrides talk, dog. And Gizmo the cat that also, so all of them override talk. Okay, and now we have some driver code to see what is what will be going, which methods are actually going to be invoked. Right, so we have a dot talk. Well, here it's pretty straightforward. Right, so the type of a is generic animal. The actual object is generic animal, so there's only one method family talk, so it's going to print noise. Right? Then this one, B is generic animal by compile time type, but it's bird by the runtime type. So the method family will still be talk. Right? Again, there's only one method family, so it's an easy example here. But the runtime type object is bird, so it will return chirp. Right? So same for cat, same for Gizmo the cat. Okay, and then here is a slightly different setup. So we have Gizmo the cat as the declared type, Gizmo the cat as their actual type, and then we have F as generic animal, and we are trying to assign G2 to it. Okay. Would that work to begin with? Generic animal, is it a super type of Gizmo the cat? Yes, it would work. So now, what happens when we call talk on F? The runtime type of F is generic animal, so we are selecting the method family talk that returns a string and has no arguments. And then when we invoke talk, we analyze the actual object, the type of the actual object, which would be Gizmo the cat, right? So it would print, hello, I would like some oatmeal, right? Because the runtime type of F is Gizmo the cat. All right, so this is going back to our struggle with duration and nano-duration, right? Remember when we accidentally, when we wanted to override equals but accidentally overloaded, so we wrote this red method, right? We created an overload, and we still have that equals that we inherited from object, and that was causing us trouble. So if you want to, override, we have to override with the exact signature of their, with the exact signature of the method that we inherited, right? So like that. All right, we have two method families here, and that was causing trouble because either this method would be called or that, depending on the type of the objects, right? So if these are duration, then this red family will be called, right? If this is an object, then the blue method family would be used, right? And that gives us all that trouble. All right, so. If both of them are object, then still the blue family is going to be used. All right, so that's that, and here is an exercise. Let's see, y extends x, so x, y, and then we have, right, so this is one hierarchy, and then we have a, b, and c, okay, we have method m, so how many different families do we have? We have two families, a red and a blue. The one that takes an object, the one that takes a z. We know that here in C, we are overriding M that we inherited from B, right? So within the same method family, we're just providing a different implementation. So there are just two method families. All right, so let's analyze their examples. This A, compile time type is A, and runtime type is B. So when we call this, which method is going to be called? Well, let's do the analysis. The compile time type of lowercase a is uppercase a. So we're only going to look at the method families in class A. So there's one. Is it compatible, right? Would that work at all? Well, let's look at O. O is an object, so yeah, it would work, right? In fact, it's a perfect match. So it is the red family, and then at runtime, we would look at the runtime type of A, and it is B. So we would be looking for a red method overridden in class B. Is it overridden? No. Which means that we would still call this M from A. Okay? So the method to be invoked would be the method from the red family, this one. Right? So now let's look at another example. Right? So here we have B and W defined like that. Again, see how it's getting complicated because we have a hierarchy of classes that our variable on which we invoke the method. And we also have a parallel hierarchy of classes for the variable that is our argument. Okay, so let's try to get it straightened out. So B, compile time B, method M. So we're only going to be looking at methods M and B. How many method families M in B? Well, there are two, right? Red and blue. Why? Because this blue does not override this red. They're different method families. They're overloads, right? That's why B would have two method families, the red one and the blue one. So which method family is going to be selected at compile time? Well, that depends on the parameter, the type of the parameter. W is W. So out of the red and blue, which is a better match? Or are they equally good? Or are they equally bad? The blue is a perfect match, all right? Just based off their compile time type. So the blue family will be selected, and now at runtime, we analyze the runtime type of their object on which of the receiver object, the object on which we are calling this method M. Right? So we have to look at B and the object that B is referring to. And it is C. So the runtime type of lowercase b is capital C. All right. So we see that yes, class C offers an override of the blue family, and this is the method that will be called. Note how it actually uses a covariant return type. Right. Y is a subtype of X. So this is valid for overriding, right? So this X, right, variable, will be accepting an object of type Y, and it is valid, right? Because X is a supertype of Y, so X can totally have a reference to an X object or to the Y object, right? That's why covariant return types are safe. That's why they are allowed. All right, subclassing can be difficult, can be full of subtle bugs. So look at this piece of code and tell me if you see any issue with this code. So let's take like 30 seconds for you to read through this code and let me know what you think about it. It's assumed, yeah, so, yeah. It has gaps, it's just not listed here, so. Yeah.
I have two theories. The first is that, doesn't he say super dot inc1 parentheses and in the override of inc2, or does that not matter?
Okay, well, let's take a look. All right, we just did our analysis. What is the runtime time? What is the compile time type of A? A. So we only going to be looking in A for N2. So there's one, right? So this is the method family, and that one will be selected. A is an A, so this N2 is going to be called. All right, so there's there's no question about it. All right, then int1 is going to be called. All right, what is this int1? Int1 is not even defined in A, but it's inherited. Right, so it will be this blue int1 because it is inherited from B. It makes its way into A. It does C++, and everything's actually looking good. Right, so there is no issue with this code. Okay, so you're given this code and you're like, all right, so I wanna optimize it a little bit, right? So why do I overwrite int2 that calls int1 here, right? So basically, see that you have to copy paste the C++, the contents of int1 and int2. So it would be a natural thing to do. Right? It's, we always, teach you, to not copy paste code. If you have code that already does what you want, just call that code. So you would be willing to do the following: basically change this int2 so that it calls int1. Right? That would be a reasonable thing to do. Right? Because you had old clients that were written against the old name of the function. Now you wanted a new name of the function, but the functions do the same thing. All right. So you decide to avoid this copy paste, and you make this very tiny change. Right. So you actually have two choices, right? Either change int2 so that it calls int1, or change int1 that calls int2. One is actually safe. The other one is exposing a big problem. So let's see what happens. Again, the driver code is exactly the same, and that's that's probably the most upsetting thing about this example. Their client is not changed. You changed something about your library. You made an improvement in your library. And all of a sudden, the client that calls int2, this is the int2, it then calls int1, this int1, which calls int2. Now the question is, what is this int2? Which object is this int2 invoked from?
I feel like it's going to invoke the one in A because it's going to first try to find over, because if you're calling from A, so it's going to go down to the lowest level and try to find the most overwritten one, and it's going to find that, and it's going to...
Yeah, so if you just say int2, it's the same as saying this dot int2, and this refers to the receiver object. What is the receiver object? It is A. Okay? So this int2 would be this int2, which calls int1, which calls int2, this int2. So you're going to get an infinite loop. All right? Very confusing. All right? Very subtle problem that is very hard to debug, right? Because it's basically going back and forth between two classes. This problem became known as a fragile base class problem. Okay? Because you make your base class, your A, fragile by just making this little change. All right? Because you think kind of intuitively that this int2 would call this int2, but no, it's not. It's going to call int2. If it's overridden, it's going to call this overridden int2. All right, very simple. All right, so this is just one example showing that subclassing can be difficult and confusing. Here is another example. Here's a set that counts the number of attempted additions. So basically, we take our baseline hash set and we want to introduce a counter that would count how many times an object was added to the hash set. All right, so we make a subclass instrumented hash set that has this private field add count, and every time we add, we increase this add count. Every time we add a collection, we increment that count by the size of the collection. All right, so is there anything wrong here? Does anyone see any signs of a potential problem? No? All right, let's look at this add all. So imagine we are calling add all with a collection of size 10. So we immediately increase add count by 10. And then we call super.addAll. Super refers to the hash set, right? So how would add all method be implemented in hash set? Well, obviously, it would go through all elements of this collection C and call add on each element of that collection C. Right? But that method add in the hash set is overridden in our instrumented hash set. So when that code in hash set, that code inside the add all method of hash set, inside the loop it calls add, it actually is going to now call our add, overridden add, which will increment the add count again. So we will effectively come up with incrementing this counter twice for every element of the collection that is added. All right, so yeah, subclassing is can be difficult. All right, so here is, and this is just an example, right? So we see that when add all in hash set, right, calls add, this is going to be our add, right? This add, okay? And not the add from hash set, but the add from the overridden add from instrumented hash set. All right, so we are adding a collection of 10 items. We will end up adding counter 20 times, incrementing count 20 times. All right, yet another problem, known as, it also has its own name, yo-yo problem, okay? So this is exactly what we have seen, right? So essentially the problem is that we have a callback, right? So this call to add is a callback, and the actual callback method is our overridden add, okay? And basically their flow will go back and forth between instrumented hash set and hash set, right? So add all is called here. It calls add all from hash set. It calls add, which goes back to our add. All right, and then the entire cycle repeats, right? Another element from add all is considered in this loop, right, which is in the add all of hash set. It calls add, which is again another our add, right? So that's going to be just going back and forth. All right, what is probably the most depressing thing is that it turns out that by making our new instrumented hash set, we sort of broke the original hash set. Okay, so now the behavior of hash sets method at all depends on our subclass. Okay, and that is, of course, very unfortunate. All right, so yeah, that was this example. All right, Interface inheritance, right? So far we mostly talked about classes. What about interfaces? Well, when we inherit an interface, we in Java don't say inheritance, we say that we implement an interface. But we can actually have an interface extending another interface. So we can build an inheritance hierarchy out of just interfaces directly. And remember, interfaces are essentially pure abstract classes, and as such, they are very useful because as any abstract class, you cannot create an instance of an interface. So you avoid this problem of inheriting methods that you do not want, right? Because there are no methods in their interface. All right, so with our example, we could have used interfaces, or we could have used composition in order to implement our instrumented hash set. Again, if inheritance does not work well for you, you're not forced to use it, right? So you can just go with composition, for example. All right, so for interfaces, if we are creating a class that will be a concrete class that provides implementations to all their methods promised by the interface, we say we are implementing an interface, right? If we are just inheriting their declarations of methods from an interface and we want to add more methods and still have an interface, we can extend an interface. In Java, there is, you mentioned this before, Java only supports single inheritance, which means that any Java class can only extend a single class, regardless of whether it's abstract or concrete, right? Only single class. But we can implement multiple interfaces. So a good approach would be to implement multiple interfaces. All right, that would basically say to our clients that we, the object, right, the class that we are defining, it has all the behavioral features of each of the interfaces that we implement. And then, if you need to extend a class, make sure that you extend an abstract class. Remember, when we extend concrete classes, we inherit implementations that we don't want and that might be causing a problem, right? So extending a concrete class is, can be problematic, right? So class has exactly one superclass, but we can implement multiple interfaces. Composition we already talked about, right? We just witnessed that properties is not a true subtype of hash table, so we shouldn't be really subclassing. We can. Java does not stop us from subclassing, but we really shouldn't. Instead, we should probably think of an alternative solution, either using interfaces or using composition. Same story with the box and bulk container. Box is not a true subtype, so we should not be attempting inheritance here, right? So, or at least inheriting from a bulk container, right? Either restructure your classes so that you have interfaces that you implement, or just use composition, right? Composition. Here is an example of implementing. Excuse me. Of how we could restructure our code from extending hash table to using composition, right? So we basically include hash table as one of the fields in our properties, and this is exactly what is called composition. And then, of course, we still want to reuse the code from hash table, and we can. For example, we can call put and get, right? So basically, our get property, set property become some sort of wrappers around the put and get methods of the hash table, right? So instrumented hash set, same story. We can use composition here, right? So create a new hash set here as a field, as an object inside the instrumented hash. Again, box, same thing, right? So we can include ball container as a field inside our box. All right, so composition allows us to reuse code without inheritance, and in many cases it is a valid alternative solution. All right, it has its disadvantages, right, because it adds level of indirection. We are, it's more tedious to write because we would be probably writing a lot of those wrapper methods, right? It, of course, does not preserve subtyping, so we are not able to enjoy our polymorphism, subtype polymorphism, but it solves some problems, so it's a viable alternative, right? So yeah, instrument hash set, if we implemented it using composition, it's not a set anymore, so no polymorphism, no substitutability, right? But in return, we can make it a true behavioral subtype of set. Java wouldn't know anything about it, right? But by using composition, by making instrumented hash set a true subtype of set, we would be able to make instrumented hash set a true subtype of set. Again, another piece of evidence that true subtyping has nothing to do with inheritance. Okay, so in fact, when we had instrumented hash set that was extending hash table, it was a subclass but not a true subtype. And when we rewrote our instrumented hash set using composition, instrumented hash set is no longer a subclass of hash set, but it's a true subtype of hash set. Okay, so that's a very interesting observation. All right, so I guess that's it for subtyping. Our next topic is generics, but of course we're not going to start it today. So